Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today I will discuss about the chapter 2 of electronic circuits. Chapter 2 is diode applications. Okay, after we finish the discussion about the semiconductor diodes, we will study the diode application in electronic circuits. There are many subchapters here. The first one is load line analysis, and then series diode configuration, parallel and series parallel configuration, and OR gates, rectifier. There are two kind of rectifier, half wave and full wave, and then clippers, clampers, Zener diodes, voltage multiplier circuits, and practical application. Okay, I will start with the load line analysis. Okay, here is the series diode configuration. So we connect the diode to the some supply, input supply. It's like we have E here. This is the battery. So this is the DC, and we have the diode, or this is the diodes. So if we would like to allow the current flow in this circuit, so the diode must be forward bias. So the forward bias is like we connect the positive terminal of the diodes to the positive terminal of the battery. This is the positive and this is the positive, and then the negative terminal of diode with the negative terminal of battery or the ground. So if you remember last time we discussed about the conductor diode, this is the p-type and n-type. For the forward bias, we connect the positive or p-type to the positive voltage and the negative to the negative voltage. So this is the forward bias. And for reverse bias, reverse bias is the positive or p-type is connect to the negative battery, and the negative terminal of the diode or n-type semiconductor connect to the positive. So this is the reverse bias. Okay. So if we have the configuration like that, like the in A, so we have the characteristic of B. Here is the kernel voltage or VK. So the kernel voltage is like a silicon is 0.7, gallium arsenide is 1.2, and then germanium is 0.3 or something like that. And this is the current flow, and this is the VD or the diode voltage. Okay, so the diode voltage is like this is the kernel voltage. If the input voltage pass the kernel voltage, so the current will flow. It's like this exponentially grows, and then the voltage, the diode voltage is stable at the kernel voltage. So we see that the voltage in this component, or this is diode, is similar, is 0.7. Okay, so we have, this is the characteristic of diode. If we connect to the circuit, like we connect it to the resistor here, we have to draw the load line, like something like this. So this is the load line. So the blue line is the characteristic of diodes, of characteristic of device, and the load line is the network or the circuits. And for the cross section with the x-axis is the E is the input supply, and the cross section with the y-axis is voltage supply by divide to the resistor, E divided by R. So we have two cross section, the cross section to y-axis and then x-axis, and then we draw a line from here, okay, from here to here, and then the cross section between the characteristic device. This is the key point. Okay, so for the key point, if we mark to the y-axis, we have the ID key, and then x-axis is VD key. So how we get this one? Because here we using this equation. It's like using the Kirchhoff plus E minus this. We using this loop plus E minus Vd minus Vr is equal to 0. So E is equal to Vd plus IDR here. So as Vd is equal to 0, it's like this one in y-axis is Vd is equal to 0. So the ID must be E divided to R. And then when the ID is 0, it means that in the y-axis ID is 0. This ID is 0 here. So the E become Vd plus IDR. So ID is become 0. So Vd is equal to E. So we have this cross sections. So this is the key point of the diode. So the intersection between two curve like this one. So we have the key point, and then we also can use using the mathematical analysis to get the ID. ID is this one, these equations. Okay, so for example 1, this is the diode characteristic of the silicon. Silicon is connected to the circuit like this one, and then determine the Vd key and ID key, and then Vr. The first one, we have to draw the load line, and then the load line is using a 2 point. The first one is in y-axis cross section, ID I divide to R, so we have the 20 milliampere here, and then Vd is equal to E when the ID is equal to 0. So this is the another cross section here. So this is the load line, the red line. I draw a red line. This is the load line. So the cross section between the load line and the device characteristic is the key point. So this is the key point. So we mark to the y-axis, we have the ID key, and then to x-axis we have the Vd key here. So Vd key and ID key is this value. And then the second question is, what is a Vr? Vr is, if we notice in the circuit, this is the Vr is here, Vr. So Vr is I this is the currents, I dot R. And I is equal to the diode voltage, the diode's current here. So I is equal to ID. This is diode current. So if we use the ID key, so ID key is 18.5 and R is 1 kilo ohm. So we have the VR is 18.5 volt. So this is the answer of the questions. And then this is the diode equivalent circuit. We already explained it in the first chapter. This is the piecewise linear model, and this is the simplified model. In the piecewise linear model, we have the average resistor here. I have discussed and I have explained about the average resistor of the diode. And then this is the simplified model. Didn't use the RF and ideal device. And the piecewise linear, we use this one for the bending, and for the ideal, if the value of the Vd is similar to Vk, and then there is the current flow. And then for the ideal device, the Vk is equal to 0. It's like this one, so it is 0, so this is the ID. So this is the diode equivalent circuits. Okay, and this is if we use the equivalent circuits for this diode. I mean that we didn't use the characteristic device. We used the ideal of diode, so 0.7, and then the current flow. So the key point is here. So the ID key is 18.5 milliampere and Vd key is 0.7 volts. And compared to this one, Vd key is 0.78. So there is some differences between the ideal characteristic and the simplified model. Okay, if we use the ideal model, so ID key is similar to the cross section between the Y is 20 milliampere. Okay, and then we start to discuss about the series diode configuration here. So this is the approximates and ideal semiconductor diode models. So this is the approximates and this is the ideal. Approximate mean that if the voltage, diode voltage is reached is similar to the phase key, the key voltage or typical forward voltage 0.7 volts, and then the current will flow, large flow like this ones. So in ideal phase key is similar to 0. So if the phase VD diode voltage is equal to 0, so there is a current here. So this is the series diode configuration. Okay, and this is the forward bias, and forward bias, the diode voltage or VD is equal to V K atau key voltage. So it depends on the diode. If we use the silicon, so V key is 0.7, silicon is 0.7, germanium is 0.3, gallium arsenide is 1.2, and etc. And then how to, if we connect it like a series, so we can calculate the VR. VR here using the Kirchhoff is E minus VD or minus VK, because VD is equal to VK here. And then ID is equal to IR, or the current flowing in the circuit is VR divided to R. And then yeah, we can make equivalent circuit like this one. So the VD here, the silicon voltage, we use the 0.7 volt here. So this is the substituting equivalent for the on diode. And then for reverse bias, this is the reverse bias. So we connect the negative polarity to the positive and positive to the negative. So there is no current flow in the diode because the depletion region will be very large. So there is no current flow in the forward reverse bias, sorry. So the ID is equal to 0. So VR here, the voltage in the resistor, also 0, because the VR is the current cross to R. Okay. So this is the for example, this is the series diode configuration. We have the supply voltage or 8 volts, and then we use the silicon, and this is the R here. Determine the VD, VR, and ID. Because this is a silicon, so VD, the on state of the diode or VD for silicon is equal to VK or 0.7 volts. And then VR is E minus VD. So like using the Kirchhoff, E minus VD. E is 8 volt and VD is 0.7, characteristic of silicon diode. So this is the 7.3 volts. And then ID is equal to IR is VR divided to R. VR is at 7.3 and R is 2.2 kilo ohm. So we have the ID is 3.32 milliampere. Okay, and repeat if the diode reverse. If reverse, so the diode is off. So there is no current flow, or ID is equal to 0. So if we use the Kirchhoff model, E minus VD minus VR is equal to 0. So VD here is E minus VR. E is 8 and VR is 0 because no current flow. So the VD here is 8 volts. So this is the 8 VD is 8 volts. Okay. And then this is the source notation. So if or in the book they write like this one, E is plus 10 volt is mean that like this one, it's minus is like this one. We inverse the polarity of the battery here. Okay, so minus 5 is mean that this connect to negative battery and positive is connect to positive battery. Okay, so like this one, if we have the series diode configurations for the figure 2.16, so this is the connect to 0.5 volts. we use the silicon diode and then resistor of 1.2. This is the 0.5 volt. So the value of the input voltage is lower than the key or key voltage of the silicon. So because the input voltage is lower, is smaller than the silicon key voltage or key, so the current isn't flow in the circuit. So the ID is equal to 0 because the input voltage is smaller than the voltage, something like that. For the silicon, this is the characteristic diode of silicon. So this is the 0.7 and then Vk is 0.7. So the value of the input voltage is smaller than the Vk. So the ID is equal to 0. And then what is the VR? So the VR is IR or IDR. So the ID current is 0. So the VR is 0. And then what is the VD? VD for the off state. So VD is equal to E. So this is the 0.5 volt. Okay. And then this is some typical forward voltage for the LED we will use in the circuits, like something like that. For the example 2.7, determine the VO and ID for the series circuits. So this is the circuit of 2.7. We have two diodes here, the silicon and the red LED. So the first one, we have to check whether the input voltage is larger than the key voltage of the silicon and the red left. So the silicon is 0.7, okay, 0.7, and red um, red is 1.8 volt. So the first one we have to check that E is 12. So 12 is larger than 0.7 plus 1.8 for the red. So we have so the diode is on. Silicon and the LED is on because the input voltage is larger than the key voltage. Okay, so after we determine that the diode is on, we can use the Kirchhoff law. Something like that. If we use like this one, so E or first E minus Vk silicon minus Vk lead minus VO, or VO here is similar to VR. This is the VO, VR. So equal to 0, like this one. Or VO is equal to E minus Vk silicon minus Vk red. So we can use this equation here. Okay, similar. So E is 12 volt, Vk1 is 0.7 and Vk2 is 1.8. So we have the total is 2.5. So VO output voltage is 9.5 volts. And then what is the current? So the current ID or IR is VR per R or VO per R. So we have VO is 9.5 volts and R is 680 ohms. So we have 13.97 milliampere. Okay, so this is the answer of this circuits. And then how if we make a reverse polarity of this one? So we have two silicons. This is a silicon and silicon, but the another silicon, the second silicon is reverse bias. So because of the silicon is reverse bias, so the silicon is off. Okay, so the currents didn't flow in the circuit. So the I is equal to 0 because the second silicon is reversed. And then so this is become the 0. And what is the VD2 and VO for the circuits? Okay, the first one may be the most easiest way to determine VD2 and VO. For VO, because there is no current, so VO is also 0. okay, because VO is ER dot R. ER is equal to ID dot R, so ID is 0 because the diode is off, so VO is 0. And how about the VD2? VD2 is this one. What is the VD2 here? The voltage in the off diode. So we have using the Kirchhoff, the similar way which I discussed before. Then we can use like this one. So E minus VD1 minus VD2 minus VO is equal to 0. So VD2 is E minus VD1 minus VO. So E is 20 volts. VD1 off is 0, and then VO also 0. So we have VD2 is 20 volts. So the VD2 here is 20 volts and VO is equal to 0. Okay, so please check by yourself. You can follow my answer here for this example. Okay, and the second is the parallel and series parallel configuration. The first we discuss about the series configuration, and the second we make a parallel of the silicon diode like these ones. So determine the VO, I1, ID1, and ID2 for the parallel diode configuration like this one. So we first we notice that the output voltage here is parallel to the diode silicon of D2 and also in the parallel to D1. And we have to check whether the diode is on or off. By using, we check the input voltage. The input voltage is 10 volts, so it's larger than the key voltage of silicons. So the two both of diodes is on. Okay, so on it means that the voltage of the D1 and voltage of D2 is similar. This is the similar to the K is 0.7 volts. So because of the output voltage is parallel to the D1 and D2, so the VO is also 0.7 volts. And then what is the current? The current is I1 here. I1 is VR per R. And then how to get the VR? We can use the E minus VD because we can use the Kirchhoff one here. E minus VD here. So 10 minus 0.7 per R is 0.33 kilo ohm. So we have the I1 is 28.18 milliampere. Okay, and assuming that the diode characteristic is similar, so we have the ID1 and ID2 also similar. This is the 20 here, like in Kirchhoff, and then we have 2 for the ID1 and ID2. So we have the similar current of ID1 and ID2 because we assume that the diode is similar with silicon. So we have the ID1 and ID2 is I1 per 2 is 28.18 milliampere per 2 is we have the 14.009 milliampere. So this is how to solve this equation. And then for this question, determine the VO for the network here. So this is the 12 volt input voltage, and we have the parallel connection of the diode, silicon diodes, and the green LED like this one. And we have to check whether the silicon and green LED is on or off by check the input voltage. Input voltage is 12 volt, and the green diode or green LED has the typical forward bias of 2.2. So we have this one, the Vk of the green diode is 2.2 volts and Vk of silicon is 0.7. Okay, so because this is the parallel, so the voltage between two diodes must be similar. The parallel is mean that the voltage is similar. So we check that the silicon diode is on if we connect to 12 volts. So this is the on. So because of the silicon is on and the diode of silicon will deliver the current here. So the voltage of the silicon will be stable at 0.7 here because the value of the Vk of the silicon is lower than the Vk of the green LED, like this one. So the silicon will be on in 0.7, but the green LED is off. If we check here, so this is the characteristic of a green LED. We have the voltage here in 0.7. When the silicon is on, LED is off. Okay, so because this is parallel, so the voltage of the green LED will be stable at 0.7. It's similar to the silicon. So this one must be similar. This line must be similar. Okay, so the green LED will be off, but the silicon is on here. Okay, so this is the off because the voltage of the green LED is 0.7 here. This is the 0.7, is similar to the Vk of silicon. So this is similar if I change the green LED to another diode green LED. So to solve this problem, we have to choose what is the lowest value of Vk, and then this is the Vk in the circuits. Okay, so how to determine the VO here? This is the VO. So VO must be, this is 0.7. So this is the off. So VO is 12 minus 0.7, and we have that's 11.3 volts. Okay, and then yeah, you can study by yourself. If I connect like this one, this is the I think this is quite, and then the explanation is quite enough to be understood by you. Okay, and then after we finish the explanation about the series and parallel application, we can use the diode for the AND and OR gates like this one. Okay, we connect a diode like this one and determine the VO for the network in figure 2.39. This is the silicon D1. We connect to the E. The input supply voltage, and VD is connected to ground like this one. Okay, so the D1 will be on, okay, because the E is larger than Vk here. Okay, so we can make an equivalent circuit like this one. For D1 connect to 10 volt and D2 connect to 0. And okay, so this is like we have like the OR gate. We have the OR gate OR like this one, OR. So if we have the input 1 and 0, so the result is 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 1. So this is the OR, typical of OR gate. So it's like we have, this is the X and Y, so this is the X and this is the Y input. So the first one, if we connect the first one with the 10 volt, so this is like 1 and this is the 0 is like 0. So the output voltage here is output voltage here is E minus Vk of silicon. So we have here, so this is the VO here. Okay, and then if we have the X is 1 and Y is 0, so we have the VO is similar to E, yeah, because if we have silicon, so VO here is 9.3 volt, very similar to the E. So it means that the result of VO is 1. If we have one of the terminal, the input terminal is 1. Okay, the output is 1. And then if we make a reverse polarity, we connect a diode 2 with the voltage like 10 volt, and diode 1 is a ground. So we can have the similar similar results, and the result is similar, is the VO is close to the ER1. And then if we connect both of the diodes to the ground, it's like X terminal, or terminal 1 is 0 and terminal 2 is 0. So there is no current flow, or there is no current here. The current is equal to 0. So VO also 0. Okay, so it is like typical of the OR. So if both input is 0, so the output is 0. And then if we connect both input is 1, I mean that this is the E is equal to 10 here. So it's similar, both of diode is on, and then we can select whether we use the D1 or D2, and then VO is similar to VO, input voltage, I mean that, so the result is 1, or 1 is 1. Okay, so we can use the diode for the OR gate. Okay, so this is for the AND gate. You can check by yourself how to use diode by using the AND gate. Similar to the OR, but we use the another character, the E here, and then this is the terminal 1, and this is terminal 2. And then for AND, this is the X, Y, and no, 0 and 0 is 0, 1 and 0, 1 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1. So if we check this answer, we can understand that that configuration can be used as the AND gate. Okay, I think for the first part of the diode applications is enough. So I will continue to the second part of the diode application. Thank you. Good afternoon. Bye bye. See you next time. Assalamualaikum warahmatullahi wabarakatuh.